Hi there! Did you know that galaxies are born, evolve, and die just like us? Their evolution and properties are determined by the environment they live in, just like a human being's personality is a combination of the traits they are born with as well as the society they grow up in. In this video, we'll discuss how this society, aka the environment, frames the life of a galaxy. Let's begin. Here, you are witnessing the simulated journey through a small region of space covered by the Gamma survey. The Gamma, or Galaxy and Mass Assembly Survey, is one of the largest multi-wavelength datasets assembled for astronomy. This fly-through shows the real positions and images of the galaxies. Here, the distances are to scale, but the images of galaxies have been enlarged for ease of viewing. This means that this is what this part of the cosmos would actually look like if we were to fly through it. Two immediate points that you would notice here are the fact that the large galaxies are quite distant from each other, and secondly, the galaxies come in all shapes and sizes, each with its unique story to tell. When people first started observing galaxies, an obvious way to classify them was through their shape, or morphology as the astronomers prefer to say. It was soon found that most galaxies are either elliptical or flat disks like a dinner plate. Advent of technology led to observations in multiple wavebands, consequently leading to color images of galaxies. In these images, most galaxies appear red or blue. Combining the two pieces of information together, astronomers came to the conclusion that red galaxies are elliptical while disk galaxies are blue. We now know that this is because the disky blue galaxies are forming stars actively while the red ellipticals are evolving passively. Also note that among the disk galaxies, while some have clear spiral structures, others are more irregular in shape and therefore called as the irregular galaxies. Universe is laid out such that all matter in the universe lies along large filamentary structures. All visible and invisible matter lies along this cosmic web. The environment is often quantified as the projected number density of galaxies. The structure of the cosmic web itself calls for three distinct yet continuous environments in which galaxies can live: the clusters, the filaments, and the voids. You can sort of imagine matter to be like dewdrops distributed along a spider's web on winter mornings. As discussed in our earlier video on the introduction of galaxies, broadly galaxies can also be classified into red and blue ones. The more massive a galaxy, the more it is affected by its environment. For instance, giant elliptical galaxies found in the centers of galaxy clusters have been shaped by the relentless gravitational pull of their surroundings. On the other hand, spiral galaxies like our own Milky Way have had a more serene existence with fewer interactions and mergers that could alter their structure. But even spiral galaxies are not immune to the influence of their environment. The Milky Way, for example, is currently moving towards the Andromeda galaxy with a velocity of 110 kilometers per second. They are destined to collide in 4 billion years, and that event will eventually reshape our galaxy's very fabric. We know that by studying other galaxies. For instance, as shown here, the morphology of galaxies evolved from low-mass blue galaxies occupying the bottom left of the plane to ellipticals in the top right. This implies that the physical properties of galaxies such as color and mass are not completely independent, or they both share a similar connection with some other parameter. And that parameter can be the environment of galaxies. As we delve deeper into the cosmos, we find galaxies that have been dramatically altered by their environment. Galaxies in clusters, for instance, have been stripped of their gas and dust due to the hot, dense intra-cluster medium surrounding them. This lack of resources have severely limited their ability to form new stars, leaving them to slowly fade away. In contrast, isolated galaxies have had more freedom to evolve at their own pace without the stifling influence of their surroundings. We know that because half a century or so ago, astronomers began noticing that while red elliptical galaxies appear in groups together, blue were sparsely placed away from them. Then, in the year 1980, Professor Alan Dressler quantified this beautifully in this most cited proof for the evolution of galaxies. Dressler plotted the fraction of elliptical and spiral galaxies as a function of their environment. In this case, he quantified the environment as a two-dimensional projected density by drawing a circle around each galaxy which had the distance to its 10th nearest neighbor as its radius. The number 10 divided by the area of this circle then gave the projected density. As you can imagine, if a galaxy is in a very crowded region of space, the distance to its 10th nearest neighbor would be smaller, and as a consequence, the density would be larger. On the other hand, if a galaxy is in a not so crowded region, often called the field by astronomers, the distance to its 10th nearest neighbor would be far away, and therefore the projected density calculated as 10 divided by the area of the circle would be much smaller. What Dressler found was profound for the times. His analysis clearly showed that the fraction of elliptical galaxies increases while that of the spirals declines as a function of the projected density of galaxies. He also studied the population of S0 galaxies, which are elliptical galaxies with a disk and are believed to be a transitional population. The S0s were found to follow the same trend as the ellipticals, albeit with a different distribution. Similarly, when astronomers split the galaxies according to their broadband colors, they found that the red galaxies are more likely to be found in the high-density environments. Refer to our video on the introduction of galaxies to freshen up your memory on the concept of broadband colors. As shown here, the fraction of red galaxies is highest in the dense regions of space, while bluer galaxies are more frequently found in less dense parts of the universe. Besides properties like colors and shapes, which are dependent on the classifier, astronomers make use of the spectra to quantify galaxies into star-forming or quiescent. As discussed in an earlier video, spectra tells us about the distance and chemical composition of galaxies amongst other properties. This information helps us to estimate the amount of new stars being formed in a galaxy and calculate its star formation rate, that is, the rate at which new stars are being formed in a galaxy. By the way, have you ever wondered why is star formation in a galaxy quantified as a rate rather than the actual number of stars? Reply in the comments below and let's discuss it there further. So, coming back to the spectra. The H-alpha line, which originates in the H2 regions, is a good indicator of star formation in galaxies. And when the strength of the H-alpha line was plotted as a function of the projected environmental density, it essentially showed the same trend of a decline in the star formation rate with increasing number density of galaxies. However, the cause of such trends were unknown at the time and are still not fully understood. But astronomers have found some clues by studying galaxies with unusual morphologies, such as those shown here. Based on such observations, astronomers have come up with suggestions of several processes which can impact the properties of galaxies. If you look closely at this montage of images going from number 1 to 6, you'll find that these different systems appear to be stages of evolution of a system of two galaxies which interacted with each other and then combined to form a larger system. This is just like studying a seed, a sprout, a sapling, a plant, and a tree to come to the conclusion that the seed will eventually grow into a tree someday, rather than waiting for that to happen for several years. And anyways, in case of astronomical events occurring over millions of years, such studies will be impossible anyways. Besides mergers, there are several other mechanisms which can transform properties of galaxies and alter their shapes. Some of them are listed here. This artist's illustration shows a spiral galaxy as it moves through a massive cluster of galaxies. The galaxy is undergoing a process known as ram pressure stripping, where streaks of bright gas are being dragged out into space by the cluster it is passing through. Ram pressure is the pressure exerted on a body because of its movement through a fluid. It is proportional to the fluid density and square of the velocity of the galaxy with respect to the intercluster medium. The stripped gas is hot and can therefore be detected using X-rays as shown in the image here. This galaxy, C153, is moving through the cluster of galaxies Abell 2125 at a redshift of 0.25. The gaseous wake is left behind as the galaxy moves through the ICM, just like the exhaust from a rocket as it moves through the Earth's atmosphere. There are many such examples of REM pressure stripped galaxies in clusters near and far. But notice that multi-wavelength data are required for such analysis. That is, images in different wavebands are a must to capture the stars as well as the gas, while spectra are required to confirm the distance to a galaxy and ensure that it belongs to the cluster and is neither in the background or the foreground of the cluster that is being studied. Some tails in RAM pressure stripped galaxies can extend to a distance of several kiloparsecs. Another environment-related mechanism which is proposed for the evolution of galaxies is strangulation. It is believed that all galaxies form inside a halo of dark matter. As the baryonic matter, which is the usual matter we are used to, loses its energy, it condenses at the center of the dark matter halo. This implies that all disk galaxies must be surrounded by a halo of warm gas which is yet to cool and fall onto the disk galaxy. During some gravitational interactions of galaxies with each other, this gaseous halo is stripped off, thereby taking away the reservoir of gas for future star formation. As a consequence, unlike RAM pressure stripping, in the case of strangulation, the star formation in a galaxy declines on a longer time scale because the gas in the disk continues to form stars. But once that is exhausted, the galaxy will not be able to replenish it, and as a result, the star formation will die in such a galaxy. Small galaxies can often be harassed by the larger galaxies. What this means is that galaxies gravitationally influence each other without going into a complete merger. In such cases, the relative velocity of galaxies in some of the strong encounters can be up to 1500 kilometers per second. But the velocity impulse felt in the interior of the galaxy is only about 50 kilometers per second or lesser. Therefore, by the time the perturbations in the disk become visible in the form of a change in star formation properties or color of a galaxy, the influencing galaxy has already moved very far away. That is why it is very difficult to observe harassment in galaxies. But simulations suggest that it is a very important mechanism transforming galaxies, especially in medium density environments such as galaxy groups and the outskirts of galaxy clusters. Here is a simulated example of a galaxy undergoing harassment. The two left panels show gas and stars in the disk from a side view, while the rightmost panel is for the stars in the disk as seen from the top. Most of the mechanisms that we have discussed persist in high-density environments such as galaxy clusters. The medium-density environments prevalent on large-scale filaments and outskirts of large clusters are very special, and we will discuss them in greater details in an upcoming video. Because remember, most of the galaxies lie on these large-scale filaments, and only about 10% of all galaxies reside in clusters, even though clusters are the most studied regions of the universe. That is because astronomers realized long back that by pointing their telescopes on these regions of the sky, they will be able to gather information about a larger number of galaxies in very small time. Note, however, that galaxies are not stationary. In fact, they are moving through different environments throughout their life. Astronomers believe that most galaxies are created in sparse regions of the space and move towards the denser regions, such as clusters and groups of galaxies under the influence of gravity. As galaxies mature and evolve by creating more and more stars and accumulating more dust and metals in the process, they use up some of their gas, while a handsome fraction of this gas is lost due to environmental mechanisms, some of which we discussed in this video. I really hope you enjoyed this little introduction to the environment of galaxies and how it influences the properties of galaxies traversing them. Do share and subscribe to our channel, and let us know what other topics you would like to be covered on this channel. Please do share our content with other astronomy enthusiasts. I'll see you next week. Until then, take care.